Aikovic equation. Okay, Aikovic equation, or you can say Aikovic equation. So when a mercury flows through the capillary, the drop get formed at the tip. If you see in the diagram below, see at the beginning there is no drop. Then the drop form, which is having smaller size, that it become bigger in size, and at the end it is falling from the capillary. Now this is a total process from here to here. Now this is a continuously happening. It happened at once. Again, same process is going to begin from here to here. Again, same process is going to begin from here to here. Okay, so this is a now cycle, you can say. This is a continuous process. Okay, so this is termed as the life cycle of a drop. This is termed as a life cycle of a drop. The time that lapses between the detachment of a two successive drop is known as a drop time. है ना, हा ड्रॉप पडलाय, ओके, पुन्हा नवीन तयार झालाय आणि तो पडायला वेळ लागतो. तो जो टाइम दॅट लॅप्स बिटवीन द डिटॅचमेंट ऑफ टू सक्सेसिव्ह ड्रॉप, दॅट इज कॉल्ड एज ए ड्रॉप टाइम. ओके, नाव as the drop grows in size, the current also increases. As the drop grows in size, current also increases. And when the drop detaches from the capillary, current quickly falls. Again, new life cycle begin. Again, drops start to form and it grows in size, so current increases. And again, drop detaches from the capillary. In this way, now this is a continuous process. So this is what the drop time to this side, and this is what the current we are observing. Okay, and this is what the ID. This is what the ID. Okay, and this is average current. We are not taking from the top. This is the Imax actually. This is the maximum current, but we are taking average. I average, and we are going to find the relation between I average and I max. Okay, that we will get. Okay, so when a drop get detached, the circuit get broken. Thus, with the increase in size, current increases. Okay, it becomes maximum when the drop is having maximum size, and when drop get detached, current become equal to 0. So that we have seen in the figure. When a polarogram is not plotted but recorded with the help of recorder pen, the polarogram obtained is not smooth. It is shown in figure earlier. Okay, it is actually that is here now. Okay, so as the current grows, it reaches to maximum and then suddenly becomes equal to 0. The lifetime of a drop, okay, during the see it becomes 0 during the lifetime of a drop. The movement of recorder plane also takes place in a forward and reverse direction. And it synchronizes with the increasing and decreasing in the magnitude of the current, and the increase and decrease in the magnitude of current depends upon the drop. Okay, so the actual polarogram we can see here. See, this is what the actual polarogram. See how the current is increasing. Okay, and what happens here, how that fluctuates. Okay, this is due to the continuous formation and detachment of drop at the capillary tip. Okay, this is what the half wave potential. Half wave potential. From here to, we can put a line. This is the half wave potential of Pb2 plus ion. Pb2 plus ion. Okay, so whenever you see such half wave potential under the conditions which are provided over here, if you observe this, you can say that yeah, there is a presence of Pb2 plus ion in the solution. Okay, this is the way by which we can identify the metal. We can identify different metal from the solution. Okay, so Aikovic equation is a fundamental equation. It links between the diffusion current with the concentration. Diffusion current with the concentration of an electroactive species. That is, you know. It is also important because all parameters related to the polarography are linked with each other by means of a single equation. The equation was first delivered or given by Aikovic starting from the basic principle. Okay, so the Aikovic equation is here now. I is equal to, it's a 607. Remember, that is a printing mistake from the book. It's a 607. Okay, this is one term, n d raised to 1 half. Second term, m raised to 2 by 3, t raised to 1 by 6. And then this is a C bulk minus C electrode. C bulk minus C electrode. Okay. When current become equal to diffusion control and it reaches its limiting value and reaches its limiting value, then C electrode equal to 0. Then C electrode equal to 0. Then the above equation becomes C ID max is equal to 607 n d raised to 1 half m raised to 2 by 3 t raised to 1 by 6 C bulk. Okay, so C electrode become equal to 0, then I become equal to ID max. When C become equal to 0, then I become equal to ID max. Okay, now what is C electrode? Is a concentration at the electrode surface. Concentration at the electrode surface, that is of electroactive species. And this is a concentration in the bulk solution. This is a concentration on the bulk solution of which of what? Electroactive species. Okay, now when this will become equal to 0, okay, so now here n is the number of electron transfer in the process for a single ion or molecule of electroactive species. D is the diffusion coefficient of electroactive species. The T is a lifetime of a drop or a drop time or time interval between detachment of two successive drops. Okay, then C is the concentration of electroactive species in millimoles per decimeter cube. Even with recorded polarigram, what can be readily measured is not ID max. Is not ID max, but we are measuring their ID average. And the relation is given as ID average is equal to 6 by 7 ID max. ID average is equal to 6 by 7 ID max. Okay, so ID average is equal to 607 n d raised to 1 by 2, m raised to 2 by 3, t raised to 1 by 6 into c. So this is what the numerical constant. This is what the significance of this for parameter. N d raised to 1 half related to the medium and electroactive species. Okay, first term refers to the reaction of electroactive species, and the second term is a diffusion. Okay, is to give the diffusion in given medium. Okay, this is for the diffusion. Then m raised to 2 by 3, t raised to 1 by 6 is also known as a capillary characteristics. Okay, and fourth part is the concentration of electroactive species. Okay, so the importance of equation is the diffusion current is directly proportional to the concentration of electroactive species. Variation in the diffusion current may be by factor. How much factor is observed may be observed as, where is my pointer? Okay, here it is. So see, okay, so due to the dependence of T, the diffusion coefficient on several factors including temperature, for all practical purposes, the equation can be written as I equal to capital I into capillary characteristics into A, where I is known as a diffusion current constant. I is known as a diffusion current constant, this one. Okay, the value of which are tabulated for a given set of conditions like a temperature and supporting electrolyte. So I is equal to 607 n d raised to 1 by 2. Okay, the value of which are tabulated for a given set of conditions like a temperature and supporting electrolyte. याच्या व्हॅल्यू ज्या आहेत त्या अवेलेबल आहेत. So limitations of the equation. When drop time is less than 3 seconds, so that disturb the solution, it causes a kind of stirring of the solution, and that affects the result which we are getting from this equation. Even the equation does not involve the temperature term, the quantity that changes with the change in temperature is the diffusion coefficient. The temperature increase in the increase in the T value is 1.5 to 2%, okay, or 2% per degree rise in temperature. So D changes how much? 1 means 1.5 to 2% change होतो with a rise in single degree or 1 degree Celsius temperature. So the equation does not hold when the concentration of supporting electrolyte is less than 50 times. Equation does not hold when the concentration of supporting electrolyte is less than 50 times than that of the electroactive species. Okay, so concentration of supporting electrolyte must be greater than 50 times than that of electroactive species. And as we know that we are using KCl as a supporting electrolyte. Okay, so this is enough for this lecture. In the next lecture, we'll see few more concepts from this topic. Thank you.